Hello everyone. Today I will cover section 16.5. I know I can finish this section and we'll go through part of 16.6. Okay, now this section 16.5 more into procedural. Most of them is about procedure. It is the curl and divergence. Now, our textbook actually start with curl and then work with divergence. In my opinion, it is easier to work with divergence first, and you will see very soon. So that's what I will do first. Okay. So I will first define. The notation upside down triangle, upside down delta. As I remember, this is the notation for nabla. This notation is defined to be an operator do x do y do C. Of course, if we have only 2 dimension, then we only use the first 2. Okay, in 3 dimension, this is a do. Now, you may wonder what this notation is about. We have used this notation in the past for the gradient notation, right? The gradient notation, for example, at that time we have a gradient of f, right? Let me write it this way. Gradient of f is equal to do f do x, comma, do f do y, do f do c. I hope you remember we used this before quite a long time ago though, maybe more than 1 month ago, when we had the directional derivative thingy, right? The directional derivative thingy. Okay, yeah. So if you think about this, the reason we can rewrite it this way is because the gradient of f basically means the gradient, the operator gradient as an operator, I think I should say, multiplied by scalar f, right? You basically distribute the function from the back, right? Okay, now that's the definition for which we used before. Now then, another definition about divergence. Let capital F be a vector field, in 3 dimension with first partial derivative axis, first partial derivative axis. So do so the divergence of f denoted by gradient dot the vector field f. Therefore, we can write it this way. This is do x, do y, do c dot f. And now suppose our vector field f, let's say that's PQR. Then we can now write that as do x, do y, do z dot PQR. Is it right? Which, due to the dot product, give us do p do x plus do q do y plus dou R dou C. Okay, so we can say that the divergence of F is basically the sum of the partial derivative of its component correspond to its position. Okay, now let's take a look on an example. I will use example from our textbook, example 4. Now you will see this part is actually on the easier side. So suppose I have this vector field here, then find the divergence of F. Well, the divergence of F, you can use div capital F with vector notation. You can also say that this is gradient dot vector field F, that this equals to the first component, the x component, you do the derivative with respect to x, plus the y component, do the derivative with respect to y, and the z component, you do the derivative with respect to z. Okay, so the divergence will be basically z plus xz for this example. I hope you find it super simple. Okay, now we will talk about the meaning of divergence later on. Okay, we will talk about the meaning of divergence later on. Now let's go on to something definition. Divergence of vector field F is 0 if and only if vector field F is incompressible. Okay, we will see the physical interpretation of divergence of F later on. Okay, that's for divergence of F. Now let's go on with curl of F, another definition. Curl of vector field F is defined to be the gradient crossed vector field F. Okay, I'm sorry, cross, not dot, cross, which we can see this way if you remember the cross product long time ago. Okay, so the first row is the vector I, unit vector I, j, k's. Now the second row is, let me play with the color so that you can see. The second row is the gradient notation, the dou x, dou y, dou c, and then the third row is our vector field position, so p, q, r. Okay, which then if we do the cross product, it will give us in the first position the x component, that will be dou r dou y minus dou q dou z. Okay, the second component will be negative of dou r dou x minus dou p dou z. Okay, and then the last component, the z component, will be dou q dou x minus dou p dou y. Okay, if divergence of a vector function give us a scalar, right? It's not a vector, it's a scalar, it's a sum of partial derivatives, right? Then the curl of F will give us a vector. Okay, in fact, the curl of vector field F give us another vector field. Okay, let's see an example. This time I will get example 1 from our textbook. Again, I try to keep it as simple as possible. Basically, I want you to memorize the procedure first. Okay. And of course, since I teach divergence and curl at the same time, then you need to anticipate that during the test you forgot which one is curl, which one is divergence. You know, just like the way in the past. I don't know if you remember when we learned in geometry, the supplemental and what's that? Complementary angles, right? Which one is which one is which one add up to 90 degree and which one add up to 180 degrees. So you may have that issue right now, but after some practice you should be okay. Now, so let's see. So the curl of f is equal to I factor I j k on the top, dou x, dou y, dou c in the second row, and then the third row is the vector field position xz, xyz, negative y squared. Okay. Now I'm not really that picky anymore at this point. You will have this type of question in your test or in final, but I still strongly suggest you every time you work with curl, because it's cross product, then write down this determinant here. Okay, write down this determinant. So the first component will be negative y minus xy. The second component will be negative of 0 minus x, and the third component will be yc minus 0, which if we simplify we get negative y minus xy, x, and then yc. Is it okay? Hold on, what am I doing? This should be negative 2y squared. Is it okay? Yeah, so that's for the curl of f. Definition: let f be conservative now. That implies there exists a potential function f such that the gradient of f equals to that vector field f. Okay, now if the vector field f is conservative, then the gradient of the curl of that vector field will be equals to vector 0. Okay, in other words, i.e. the curl of the gradient of f will be vector 0. Okay, now we will see the interpretation. Again, we will see the interpretation of divergence and curl later on. Okay, but one of the big issue is then, so if vector field f, which consists of PQR, 2-dimension instead of 3-dimension, is conservative, then how do we find the potential function? the potential function. We will do this with example from our textbook again. Okay, I see that in example number 3. Suppose we have this vector field, show that it is conservative. How to show that a vector field is conservative, as we have seen in the previous theory, then the gradient in part A, what you want to do is you find the curl of f and show that the curl of f is 0. Okay, the curl of f is 0. So that's the I, J, K of dou x, dou y, dou c of y squared z cubed, 2xyz cubed, 3xy squared z squared. That is equal to the first component, that will be 6xyc squared minus 6xyc squared. The second component will be negative of 3y squared c squared minus 3y squared c squared. And the third component will be 2yc cubed minus 2yc cubed. And you can see this is basically vector 0. Okay, consequently, the vector field is conservative. Okay. Now, then how do we find the potential function? So once we know that the vector field is conservative, then we will try to find the potential function. Now, notice that the gradient of f is how to say that? The derivative of the partial of f respect to x, the partial of f respect to y, the partial of f respect to z, which is equals to the vector field f, right? Which means if I want to find the potential function f, we have 3 points of view. First is the integral of p respect to x, integral of q respect to y, and integral of r respect to z. Okay, now for this question here, we can do it in any order though. Okay, you can do it in any order. Now I will do this question, example 3b, 2 times. The first way is our textbook way, which is basically the following. Basically what it is doing is from P, this is the scheme, okay? If I just do the question right away, you may get confused what I have been doing. So from that x component of the vector field, I will integrate that, I will get f, okay? Now, but this f here may have some component that is not anticipated in P. So I do the derivative respect to integrate respect to x. Okay, and then later on I will do the partial respect to y and set it equals to q. And there's something I need to equate there. Okay, something I need to equate there. And then after that, I integrate that again to get a more complete view of f, which I will do the partial respect to z, okay, and match it with r, and then from there I will integrate that again. Okay, integrate r respect to z. Okay, so the procedure seems to be very long. Okay, bear with me though, bear with me. Okay, let's start with p. Our p x y z is y squared z cubed, right? Okay, so the potential function f x y z must be the integral of p dx. That's integral of y squared z cubed dx. That's xy squared c cubed. Right? Now, the thing is, because we integrate with respect to x only, then the integral may give us a function that is not dependent on x. Is that right? Including constant. Because if we do the derivative of this guy respect to respect to x, then we will get the p, right? Okay. In other words, there's a family of functions, not a single function, but a family of functions whose integral of p is this guy. Okay. I think I should say the integral of p gives us a family of function instead of a unique function. Okay. Now then, the thing is, when I do the partial of this f here, the partial of this f x y z with respect to y, I will get 2xyz cubed plus the partial of that g1 of yz with respect to y. Is it right? Okay, now match this with q. You match that with q, which is 2xyz cubed. So that's 2xyz cubed. Okay, now notice that it means the partial of g1 with respect to y is 0, right? So what is the integral of g1 x yz with respect to y? I think I say it wrong. I think I say it wrong. I want to say that the integral, then g1 of yc will be the integral of 0 dy. Is it right? Okay. Now, what is the integral of 0 dy? Is it just a constant? Actually, it's more than that. Notice that it may be also a function of z, right? So this is a function of z only. Okay. In other words, if we look back here, okay, now our potential function x, y, z is equal to x, y squared z cubed plus g to z. Okay, now we do the derivative, the partial again of this function respect to z. That will be 3xy squared z squared plus the partial of g to z respect to z. Now we need to match that with r. Okay, now when we look at r, what is our r? 3xy squared c squared. Three xy squared c squared. Is it right? Okay. Now that implies dou g2, which is a function of c only respect to c, equals to 0. Okay, now from there we can say then g to z at most is a constant. Let's call that k instead of c. Okay, now then going further, the potential function f x y z must be x y squared z cubed plus k. Okay, now that's the first method, but I want you to see that this is actually the correct way to do that. This is the definite proper way to do this. Now I want to teach you a shorter cut, okay, simplified version, but you need to be a lot more careful. Simplified way, in which the potential function is basically the integral for of each p dx, q dy, and r dz. Okay, what is my p again? Y squared c cubed dx. When I integrate this, then I will get xy squared c cubed plus g1 as a function of not x anymore, but yz. Right? Because you integrate it with respect to x, any function who is dependent on yz only will become 0 if you do the partial respect to x. Okay, now how about the q? How about the q? The q is 2xyz cubed. 2xyz cubed dy, that will give us x y squared c cubed plus a function dependent on x and c. Okay, you know what? I want to make sure that this g1, g2 here is not misunderstood as the same g1, g2 we have earlier. So let's call this h1 and h2 instead. Okay, and then integral of r respect to z. What is our r again? Our r is 3xy squared c squared. 3x y squared c squared dz, that gives us xy squared c cubed plus a function of xy. Now then, from here we notice that these three expressions here are exactly the same one, right? But we don't have a function depends on yz only. We don't have a function depends on xz only. We don't have a function depends on xy only. So the consequent must be then the function of xyz must be xy squared c cubed plus constant. Okay, now of course I don't really like this example here because it doesn't really show the complexity. Okay, so what I want to do now is to find to do another function, another vector field that is conservative, yet mm, yet maybe the function may not be that simple. Let's say this one here. Okay. Is this conservative to start with? So let's see. The curl of vector field F will be ijk dou x dou y dou z of 1 sine z y cosine z. That will be cosine z minus cosine z negative of 0 minus 0 and then 0 minus 0. Oh, okay. So this is actually equals to vector 0. Okay, so it means this vector field is conservative. Once we know that it is conservative, then we will look for the potential function, right? So let f be the potential function. Then f x y z is the integral of 1 dx, right? Okay. Oh, I'm sorry. Integral of 1 dx. That will be x plus a function of yz. Is that right? Okay. Now, and then if we integrate with respect to the second component q, the sine z, respect to y, then that will be y sine z plus a function of xz, right? And then when we look at the third component, integral of y cosine z dz, this will give us y sine z plus a function dependent on xy only. Okay, now let's group them. Notice that we have y sine c in the last two, but in the first one we don't. Well, because y sine c, from there we say, oh yeah, y sine c must be this h1, right? Okay, now x is not feasible in the second and third, but it is actually a function of x, which is part of that h2 and h3. Okay, so consequently, then the potential function xyz must be y, maybe I start with x plus y sine z plus constant. Always don't forget to plus the constant. Okay, that's a simplified where you need to simplified method in which you need to do some matching thingy. Okay. Now the last part of this section is something we will see much later. It's about factor form of Green's theorem. Let C be a curve. Oh, you know what? Before that, I just realized one thing. Okay. Did I mention that earlier? Actually, before I go to the factor form of Green's theorem, I have something that I need to say. is this one here. Quite important though. Let me just quote that theorem. Okay, let me just quote that theorem. We have this theorem here. If F is a vector field and P, Q, R have continuous second order partial derivatives, then the divergence of the curl of that vector field must be zero. Now notice that this PQR, the vector field, may not be conservative. Okay, the PQR may not be conservative, but the divergence of the curl will still be equal to zero. Okay. Now, but of course, it works for conservative, right? If the F already conservative, then the curl of F is vector zero. Okay, and of course, the divergence of vector zero is just zero. Right? Now, but what this theorem actually says is what happens even if F is not conservative, but has continuous second order partial derivative. Okay, then you will see it has something to do with Clairaut's theorem. Okay, you will see it has something to do with Clairaut's theorems, and therefore the divergence will end up being zero. Okay, if we want to take a look, let me copy paste something. Where's my formula? Okay, let me copy paste from the curl of F. Oops. Let me insert first. Yeah, this one here. This is the curl of F, right? Okay. So what if I apply? Let me use green color. Oh man, I think I would just keep. Let me use black color then. Okay. So the divergence of curl of F that is equal to dou x of dou r dou y minus dou q dou c plus dou of dou y, actually minus because of the negative, of dou r dou x minus dou p dou z, and then plus dou c of dou q dou x minus dou p dou y. Okay, now remember, if the second order partial derivative is continuous, then Clairaut's theorem apply, right? Clairaut's theorem apply, which means the mixed partial derivative will be equal regardless the order. Okay, so this will be dou squared r dou x dou y minus dou squared q dou x dou z minus dou squared r dou y dou x plus dou squared p dou y dou c plus dou squared q dou c dou x minus dou squared p dou c dou y. Okay, by Clairaut's theorem, the mixed partial derivative are equal regardless the order. The order of differentiation. Okay, regardless the order of differentiation. In other words, this guy here will cancel this guy here will cancel this, and this guy here will cancel this. Okay, and therefore we get equals to 0 as we expect. Okay, so is it possible for us to have a vector field whose divergent curl of that vector field is not 0? It is possible. It is when the PQR does not have continuous second order partial derivatives. Okay, if PQR has second order partial derivatives and they are continuous, then the divergence of the curve have to be 0 by Clairaut's. Okay, we use this later on though. Now let's continue with vector form of Green's theorem. Let C be a curve enclosing D. On xy plane. Okay, now remember Green's theorem was like on xy plane only, right? It's on two-dimensional. Okay, so our C originally is RT equals to the x component, the y component only, right? Now we will see it this way. We'll see it that way. Now, this is, if you think about it, this is basically the idea of augmentation. Like it's supposed to be two-dimensional, but we see that from third dimension, and you set the third component to be 0 or any constant actually works. Okay, and let vector field F be vector PQ, which we will now see as vector PQ0. Okay, so you make the third component, which was not existent, now becomes 0. Okay, now you will see then we can now rewrite our integral over closed curve C of f dot dr. Now, originally supposed to be double integral over d of q sub x minus p sub y dA, right? Okay, now, but notice that the integrand is actually the third component of the curl. The third component of the curl. That's the integrand, right? This is the curl of f. That's the third component of the curl. Is it right? Okay. Okay. So how to pick the third component from the curl? What we will do is you take the curl of that vector field, but then you dot that with the unit vector on the of the third one. Okay. Now, what is important here? What is important here later on when we see a more general form of Green's theorem, in much later in 2 sections ahead of this, you will see that we can apply Green's theorem even in 3 dimensions. But when we apply the curl, it will be dot with the factor normal to the plane. This is the normal factor. That's the factor normal to D. Okay, I think I should say instead the unit factor normal to D. Okay, now, do we this now? No, we don't really need this now, but we will see that later. Okay, now suggested homework from here is suggested homework from this section 16.5 will be from number 1 to number 8, 13 to 18, 20, 22, 30 to 32. Okay. I would like now to explain to you or try to help you with understanding what is the divergence and curl of F. What do they represent? Okay, so let me share my screen now to YouTube. Okay. We have here that, roughly speaking, divergence measures the tendency of the fluid to collect or disperse at a point, where the curl measures the tendency of fluid to swirl around the point, to go rotational. Okay, I know I have some good video about this in the past. Let me look for it. I think it's this one. Yeah, this is the curl in 3 dimension, right? Okay, so if you see from above, for example, okay, the curl at that point is actually it's actually rotating like this. Okay, that's a rotating vector field. Now, let's say I think this is a good example. Suppose we have a vector field as we have seen above, right? And then we want to see what happened at a certain point. If you have a point right at that vector field, right? What happened to that point? Now, the point may be being pushed by some vector field, but beside being pushed, the vector field, a ball at that point may be rotating also. Okay, the ball at that point may be rotating also. Now let's see what happened if I move this ball here. Notice it is still rotating that way. Okay, but it is because of the following. Let me graph that for you. Let me graph that for you. Going back to our graph here. Imagine if I have that kind of vector field. Let's say I have vector field like this. It's a linear vector field, but then the one below that it's stronger. Okay, the one above that is weaker. Now, what happened then if you have an object here? Now notice that the force field, the force that is pushing that circle or that sphere at the lower part is stronger compared to the force at the upper part. So what happened is if you push this side here stronger than this side, automatically then the sphere will rotate this way. Okay. On the other hand, if the sphere is being pushed, like the top one is stronger than this one here, the bottom one, then of course the ball will spin this way. Now, if you play ping pong, okay, and you know, like if you spin the ball, right? If you play ping pong, then you actually see that you see that effect. Okay. Now, in fact, if you let's say this is your ping pong, right? And then you spin it, let's say in that direction. At the same time, you hit it that direction. So not only the ball goes in that direction, but it along the way it also spins. So you will see that it actually spins sideways, like that. It's not. It will not go in the straight direction. Okay, it will be straight according to the direction of you hitting the ball, but because there's some spinning to it, instead of going straight, it's actually going like curve, like this. Okay, that's what happened to that ping pong ball. In fact, if you are a big fan of soccer, which I am, right, even though I don't really follow them anymore recently, you know, sometimes those keepers, the goalkeepers, they need to be careful with that kind of spin ball, because uh, Ronaldinho may be kicking the ball in a certain way such that, let's say this is the goal, okay, and somebody's here kicking the ball in that direction. Don't you think that, oh, originally it is in the direction, then it will go that way? No, because if the ball is actually spinning, it may spin in. Notice that the trajectory now changed because of the ball being spin. Okay, so the kicker, the free kicker, for example, the person who do the free kick, right, will kick that in certain ways such that at the beginning of the trajectory, it seems like the ball will not go in, but because of the spinning is invisible, right, hard to see, then it may curve. Okay, you call this a curveball when you play what softball, maybe, right? You call that a softball, curveball. In Indonesia, the term the if you translate that, we call this banana kick, because it bends like a banana. You know, it's banana kick. Okay. Now, what makes it happen is because of that curl is not zero. Okay, because the curl is not zero. Now, in fact, more things can be said about the curl. Okay, let's go back to that A plat here. You see that we have that curl, right? Now, notice that a curl is a factor, right? A curl is a factor. Now, that factor is actually represent the axis of, it actually represent the axis of the rotation. Okay, the curl as a factor tells us the axis of rotation. Now, and then the magnitude of that curl tells us how fast it actually spins. Okay, so suppose you have a curl. Let's say the curl is vector field F is 0, 0, 3. Okay, it means, let's say at this point the curl of that is 0, 0, 3, means this is the axis of rotation of that sphere. It actually spins this way. Okay, compared to 0, 0, 1, it means this sphere is rotating 3 times faster with the same axis of rotation. Okay, so the curl of F tells us the axis of the rotation of yeah, of the ball of the sphere there. Okay. Now, some important presentation possible misunderstanding. The picture can be deceiving. We use a sphere just as an illustration, but the curl of a vector field F actually the rotation at the point, not as a sphere. It's actually at the point. Okay. Now, next, how about divergence? Let me see. There must be some divergence. Yeah. How about divergence? Divergence tells us if something will be expanding or shrinking. Okay, so if you see this vector field here at that ball, notice that the vector field around that ball will make that ball expanding. Okay, if we go back to our picture here, let's say you have a vector field like this. It gets bigger and bigger. As it goes away from this point here, it goes stronger and stronger. So what happened to an item that you place here? Now notice that the vector field to the left of that ball will push that ball becomes smaller, right? Okay, but notice that the vector field going into that ball is actually has smaller magnitude compared to the one coming out from that ball. Okay, so not only this ball later on will move to the right, okay, but along the way it also gets bigger, gets bigger like that. Okay, why? Because the push from the left, okay, which is supposed to make it smaller, right? But that push from the left, has less magnitude compared to the push going out from that. Okay, so what happened is, suppose I think the best illustration is like this may not be as nice, but you see this a lot. Do you notice that if you are washing dishes, right? Okay, when you wash dishes, the water actually fall from your from the source of water, and then it's splashed on the surface of the sink, right? Now, if you drop some ink somewhere here, okay, with that kind of vector field, how the water being dispersed, then you expect this ink later on gets larger and larger, right? On the other hand, if you see the whole of that sink, right? You have a sink here, okay, and then the water is actually sinking in. If you have an ink originally like this, okay, notice that because the vector field is actually sinking into that, right? Then eventually this circle here, this maybe I should say that this shape ink, whatever color it is, will eventually becomes longer and narrower. You see that? Okay. Now, of course, it depends on how strong is the force field, though. Okay. Yeah, but suppose this part here is stronger compared to that part, then it will get elongated. Okay. Now, in short, the curl has something to do with the rotational effect on the fluid, while divergence has the comprehension or expansion of the fluid. Okay, that's what they mean. Now again, you can go back to this link that I show you here. Okay, I think this is the one I have been using for a long time. Of course, feel free to also go to YouTube and type divergence and curl and see what other people say. I believe they will also tell us about the same thing about the rotational property and expansion property of the fluid. Okay, that's for this 16.5. We will go on with 16.6. Okay, let's go on with the next section, section 16.6, parametric surfaces. Parametric surfaces and their areas. You will see that this section is quite new for us. We have learned in the past, we have learned surfaces. We have learned the area of a surface. However, this section is dedicated for a more general approach compared to what we had before. What we had before are surfaces like Z managed by X, Y, for example, right? And then, for example, if we want to find the surface area, the area of the surface, then we use double integral over domain D of square root of 1 plus f sub x squared plus f sub z squared sub y squared dA. Those kind of magic before. Okay, but notice that this is only if we can only apply this if the function, the surface is managed by C as a function of x and y. Now, what happens if the surface is actually not a function of x and y? Let's say, for example, if the surface we're dealing with is actually a sphere. Okay. Now, definitely a sphere, however you look at that, will not be a function of only x and y, right? But it is a sphere, though. A sphere is two-dimensional. Okay. In a how to say that? A sphere, we cannot ask the volume of a sphere. We can ask the volume of a ball, because a ball means you include the interior, right? But a sphere is just the skin of a sphere, of a ball. Okay, it has no volume. Okay, just like a line has no area, it has length but it has no area. Okay, then a sphere has area but it doesn't have volume, right? Okay, so if you rely on the fact that, oh, you have z as a function of x and y, then you need to account for the point on the top and also at the bottom. In other words, a sphere x squared plus y squared plus c squared equals to 4 cannot be re-expressed using one single function of z. You cannot say, oh, z equals to square root of 4 minus x squared minus y squared. Because if you write it this way, then you will only get the top half of that sphere, not the bottom half. Okay. Now, if you insist doing it that way, then you need to do 2 times. You need to treat with the top and treat with the bottom. Okay, and the not so nice part about this, if you rewrite it using this function, is the partial derivative may not be the partial derivative respect to x or respect to y may not be continuous at some x and y. For example, c sub x will be negative x over square root of 4 minus x squared minus y squared, right? It will not be continuous at, for example, 2 comma 0, right? If you plug in x equals, you plug in xy 2 comma 0, it will be undefined. However, we know we have a point there, okay? We have a tangent plane there, but it is not the method we have before, z sub x, c sub y method, is not powerful enough. Okay, so this section is dedicated to deal with a more generalized situation. Okay, now what makes it difficult is that we then go back to the drawing board, okay, the basic idea. Okay, now, but before I get to the ideas of parametric surfaces, let's go back even further to parametric curves. Okay, so the idea, if you remember, recall parametric equation of a line in factor form, or sometimes we just call that factor equation of a line. Okay, RT equals to R naught. That's the point contained in the line. It's the R naught. Okay, plus T times R1, where R1 is the direction factor. Okay, now then depends on what is your T, then that's how long you extend your R1, right? Okay, so R0 plus minus R1, it actually refers to this point here. Okay, refers to this point. For example, as you move your T's, then the position will actually move along this line, right? Okay. We also have in the past factor function. As opposed to factor field. I'm sorry, I think I say it wrong. Yeah, factor function, you know, RT. Factor function RT. RT, where the x component is a function of t, the y component is a function of t, and the c component also a function of t. This gives us a curve in space, right? As t progresses, then we get that curve, right? Okay, so that's the line, or even the curve, which are one-dimensional. Now, suppose we go to parametric equation of a plane. Now, notice that a plane can be built using two factors. Okay, so let's say the plane contains P naught. Maybe I used regular color. Contains coordinate P naught. Okay, and parallel to factor R1 and R2. Okay, so imagine that you have a position factor R0 that goes to P0, P0. Okay, and then using that factor R1, let's say you shoot in this direction, R1. As you extend R1, then your factor will gives you a line, right? Maybe let me use blue color. Give you a line. If your T actually increasing, then R1 get extended, right? If your T is negative, then it goes backward. Okay. Now, but at the same time, it is also parallel to R2. Let me use different color. Let's say I use this one here. Ah, no, it's almost the same color. Maybe the blue, light blue, no, or this one. Let me use this one. Okay, let's say the R2 actually looks like this. Okay, so it goes this way. Okay, this is our R2. Eventually, as you play with R1 and R2, you will get this kind of grids. Like that. Okay, so for example, a point here, you may express that, oh, this is actually R0 plus 4R1 plus 1R2, like that. Okay, in general, we now can express our surface using two variables. Let's call it surface R TS, where it is R0, that's the position factor that contains P1, plus T time R1 plus S time R2. Okay. Now, our textbook, I think it's wise enough for them to actually, instead of using T and S, so I use T and S here basically with the idea of this is basically the extension of the curve that we have in chapter 14 or chapter 13. Okay, so in chapter 13, we have R0 plus TR1. Now you want to have a plane, then you will plus SR2. Like this. Okay, then it gives you a plane. Okay, so that's the reason I use T and S. Our textbook, for another reason, use UV. So let's just follow our textbook so that when you read your book, it's easier for you. Okay, we can write this as R0 plus UR1 plus VR2. But when you write the U and V, be very careful not to make them look very similar. Okay, I always suggest my students to write the U like this with some tail here and your V without tail. Now, some students, they write the U this way and their V is like this. Now, eventually you will see U and V, you will get confused with your own writing, U and V. Okay, now try to write it in a way that you can distinguish which one is U, which one is V. Okay. Now, of course, then when we have a parametric curve, right? Okay, so curve surface R U V, you can also see that as follows. Like, let's say you have a curve, right? That is managed by U. Okay. But then for each of that point on that curve, you have another curve. So you still have surfaces, right? You still have surfaces, but the grids are not straight. You see that? Okay. It still gives you surface though. Okay. Well, anyway, so you will see our RU phi right now, the surface that we are talking about in this section, will be given by x as a function of u phi, y as a function of u phi, z as a function of u phi, if we write them in vector form. Okay. Let's say for example, now this section is new for us. Okay, so be patient with this. And one of the key method to be successful in this section is by exposing yourself to some common surfaces, which is different from what we have in chapter 14. Okay, for example, well, for u phi equals to 2 cosine u phi and then 2 sine u. Can we imagine what it looks like? Okay, can we describe that? Okay, notice that description. You take a look at the x component is 2 cosine u, and the z component, which is 2 sine v, 2 sine u. If we put them together, x squared plus z squared, that is equals to 4. Okay, so on the xz plane, it is actually a circle with radius 2. Right? But don't forget, this is not two-dimensional surface, it's three-dimensional surface. So if we see that in 3 dimension, it's actually the cross section will be a circle, right? But then this y component is independent. Okay, so if we graph that later on, it actually gives us a cylinder. To be more precise, it will give us a circular cylinder parallel to the y-axis. Okay, now notice that this surface here is a function of u and v, but it is not a function of x and y. Right? You can pick a coordinate on x and y and you have 2 possible z's. Then it is not a function of x and y, right? Okay, but the way we write the equation here, the function for the surface, enable us to see that as a function of u and v. Okay. Another example, I take this from example 4. We go backward. Suppose we have, and this is actually a classic example though. Suppose we have surface x squared plus y squared plus z squared equals to a squared. How do we write this surface as a function? Now, method number 1. You may solve for z equals to plus minus square root of a squared minus x squared minus y squared, right? But because of that plus minus, then z is not a function of x and y unless you insist to split them into 2 separate functions. So the surface for the top and the surface for the bottom. The sphere on the top, let me use that notation. This part of the sphere on the top and sphere at the bottom, which is square root of a squared minus x squared minus y squared on the top, and at the bottom we have negative square root of a squared minus x squared minus y squared. Okay, now notice that even if I try to use polar coordinate system to do that, or in 3 dimension we call that cylindrical coordinate system, you end up with z equals to plus minus square root of a squared minus r squared, right? In other words, the surface on the top is given by z equals to square root of a squared minus r squared, and the surface at the bottom is given by c equals to negative square root of a squared minus r squared. Okay, now method 3, it seems to be complicated, right? But it turns out that we can perfectly get the sphere by using spherical coordinate system to describe that. Okay, we set our x equals to a sine phi cosine theta, our y equals to a sine phi sine theta, and the c is a cosine phi. Okay, or if we use a surface vector function r theta phi, then we will get the x component a sine phi cosine theta, a sine phi sine theta, and a cosine phi. Is it right? Okay, and we can say that the theta is from 0 to 2 pi, the phi is from 0 to pi. Okay, now notice that the shape of that surface is a sphere, right? If you use the rectangular coordinate system, it doesn't give us a function. You need to describe that using 2 separate functions. Likewise, if you try to use a cylindrical coordinate system point of view, you still need to rewrite that as 2 separate functions just to get that sphere. But method number 3 turns out to be give us a single function, surface vector function, okay, which we can have easier way to play with. Okay. Now, of course, some surfaces can have multiple surface parameterization. Okay, for example, let z equals to square root 2 square root of x squared plus y squared. Now, this gives us the top portion of a cone. Because the c is positive, right? Okay, so we can write that parameterization using xy equals to x comma y comma z, which is 2 square root of x squared plus y squared. Okay, you will see this is basically the way we do it in the past in chapter 15, I think. Okay, or chapter 14. In chapter 14. Okay, but we can also play this way. We say, oh, you know what? Let's make it polar. So the r depends on the r and theta, where the x is r cosine theta, the y is r sine theta, and you will see the z, if I plug that in here, I will get 2r. Where the where the theta is from 0 to 2 pi. Okay. In other words, surface parameterization, just like curve parameterization, is not necessarily unique. Okay. Now, how about tangent plane? suppose we have the issue of tangent plane. Suppose I have a curve, not a curve, a surface. Okay, and we want to observe that at this point here, right? And we have a factor normal to it at that point. That's the normal factor. Okay, and then the plane tangent to that point, maybe something looks like that. Okay, this is the tangent plane. Now, in the past, recall that suppose our z equals to c sub xy, then the normal factor will be this normal to the tangent plane. And this normal factor is the cross product of 1, 0, z sub x by 0, 1, z sub y. Now you will see a more general situation than this. Okay, and the cross product will give us negative c sub x, negative c sub y, 1. Okay, now our surface is parameterized using u and v. R u v, okay, as x function of u v, y as a function of u v, and z as a function of u v. Now you will see that the partial of r respect to u will be dou x dou u, dou y dou u, dou c dou u, okay, and dou r dou phi is dou x dou phi, dou y dou v, and dou c dou v. Now, the factor normal to the tangent plane, therefore, is the cross product of those. Okay, that will be dou r dou u cross dou r dou phi. Okay, or we may just use the subscript notation r sub u cross r sub phi. Okay, let's do an example. Example 9. Let's see, let me copy paste from the book. Example 9. Find the tangent plane to the surface with this parameterization at point 113. Okay, so our surface parameterization RU phi is u squared, phi squared, u plus 2 phi. Okay. Let's try to find what is the u, what is the phi for that coordinate. Okay. So my first step is r u phi equals to 113. It means u squared equals to 1, phi squared equals to 1, u plus 2 phi equals to 1 also. I think you can see that either u equals to plus minus 1, plus or minus 1, the phi will be plus minus 1, but then which one will give us, give u plus 2 phi equals to 1? U plus 2 phi equals to 1 when both u and phi equals to 1, right? Okay. In other words, the coordinate that we are looking for in terms of u phi is R11. Okay, the u equals to 1, the phi equals to 1. Next, we need to find the partial derivative of that factor, surface vector function u r with respect to u. That will give us 2u 0 1 r sub phi partial respect to phi will be 0 2 v 2. Then the cross product will be negative 2 phi, negative 2 phi, negative 4u, and 4u phi. Okay, so what is the factor normal to the surface at that coordinate? And that will be at 1, 1, right? At 1, 1, that will be negative 2, negative 4, 4. Okay, now this is the factor normal to the plane. Okay, and then the equation of the plane, equation of tangent plane is given by the negative 2 times x minus 1 plus, and actually minus 4 y minus 1 plus 4 c minus 3 equals to 0. See, right? Okay, and then I think we can reduce by 2, huh? We can reduce, let's reduce by negative 2. So if I reduce by negative 2, then I will get x minus 1 plus 2y minus 1 minus 2z minus 3. So that's x minus 1 plus 2y minus 2 minus 2z plus 6 equals 0. So x plus 2y minus 2z equals to negative 3. Okay, so that's the equation of the tangent plane. Now, how about the surface area? How about the surface area? Now, let the surface S be managed by R u phi, where the u phi is inside the domain D. So imagine you have that surface S, right? This is surface S, but the domain is D. Okay, now then the surface area, the area of surface S is double integral over D of the magnitude of the cross product. We actually had the special case in chapter 14 for this. In chapter 14, we actually have this in chapter 14, just to remind us. In the past, for z as a function of xy, we get what is that? Normal factor of 1, 0, c sub x cross 0, 1, c sub y. Remember, this actually gives us the area of a small tile. The area of small tile. Like let's say this is the surface, right? Maybe a bit bended, and that gives us the area of a small tile. This area here, this tile, the area of this tile here, and the area of that tile is equal to the length of this normal factor. Okay, now so to find the total area of that surface, we basically add up the area of those small tiles together. Okay, which at the time that gives us because the cross product gives us negative c sub x, negative c sub y, comma 1, then the magnitude is square root of 1 plus c sub x squared, c sub y squared. Okay, now that's the special case if the surface s is z as a function of x and y. But what happens if the surface is parameterized using u and v? And then this will be the formula. Okay, let's do some problem from here. Okay, because the key is really being used to it. Okay, the key is being used to it. Oh yeah, you know what? I need to do some example. This is from example 10 in our textbook. And you will see this surface a lot. So let's actually talk about this. Find the surface area of a sphere with radius a. Now, we know what's the surface area of a sphere. The surface area of a sphere is 4 pi r squared. In this case, because the radius is a, then it will be 4 pi a squared. Okay, now, but I think it's not about the surface area of a sphere. It's about how do we do that using parametric representation of that surface. Okay, now here we represent this surface by the parametric, the spherical coordinate system method. Okay, but because it's supposed to be rho sine phi cosine theta, right? Okay, rho sine phi sine theta, and then rho cosine phi, right? Usually, but because the radius is a, then we change the rho becomes a. Okay, so instead of giving us a ball, let's say, it will give us a sphere. Okay, now the setup is actually painful, but let's do it at least once, right? Let's do it at least once. So r phi theta equals to a sine phi cosine theta, a sine phi sine theta, and a cosine phi. So r sub phi will be A cosine phi cosine theta, A cosine sine theta, and A negative A sine phi. And the partial of R respect to theta will be negative A sine phi sine theta, A sine phi cosine theta, and 0. So the cross product R phi cross R theta is equal to, let's see, the x component will be A squared sine squared phi cosine theta. Okay, the y component will be is this guy times this, which is 0, minus this guy times this, right? But we need to take the opposite though, right? We need to take the opposite because that's the second component. So that will be A squared sine squared phi sine theta, and then the x component, the z component will be A squared cosine phi sine phi cosine squared theta plus A squared cosine phi sine phi sine squared theta. Okay, but notice that if we factor the A squared cosine phi sine phi out, then we end up with this guy plus this guy, which is 1, right? Okay, so that's A squared sine squared phi cosine theta, A squared sine squared phi sine theta, A squared cosine phi sine phi. Man, that's painful, huh? But be patient. We are in Calc 3, right? You don't expect something that easy to do. Now, by the way, notice that each component has common factor A squared. Let's pick that out. So that's sine A squared times the factor of sine squared phi cosine theta, sine squared phi sine theta, and then cosine phi sine phi. Okay, I actually write this wrong, supposed to be theta here. Then what happened to the magnitude? The magnitude of R sub phi cross R sub theta, that's equals to A squared times the square root of sine squared phi cosine theta being squared plus sine squared phi sine theta being squared plus cosine phi sine phi being squared. Okay, now I will just do it fast forward. This will give us the first two terms. When you add them, it will give you sine to the fourth theta plus the last term is sine squared phi. I'm sorry, should be sine to the fourth phi, not sine to the fourth. Sine squared, and then the second term will be sine squared phi cosine squared phi, whose common factor is sine squared phi, right? under square root, that will be sine phi square root of sine squared phi plus cosine squared phi, which is 1. Okay, so how about the surface area? The area of that surface S will be integral, double integral from 0 to 2 pi for the theta, from 0 to phi for the 0 to pi for phi of a squared sine phi d theta. Notice that the domain of integration is quote unquote a rectangle and the integrand is separable. So this is basically integral from 0 to 2 pi of d theta times integral from 0 to pi of a squared d phi. I'm sorry, a squared sine phi d phi. Okay, the first integral gives us 2 pi, the second integral gives us a squared. Am I missing something? We're supposed to get 4, right? Hold on. Supposed to be 4 pi a squared. Am I missing something somewhere? What am I missing? Oh, I'm sorry. Integral from 0 to pi is 2. Duh, I forgot the 2. So this is integral from 0 to pi over 2 of sine x dx is 1. So that's the area in the first quadrant. The area in the second quadrant also 1. Okay, for sine. Okay, so yeah, that's supposed to be 2 instead of just a squared is supposed to be 2a squared. That gives us 4 pi a squared. Okay, so that's the way we use this formula here. But actually I want to say something even more specific for this case. If you remember, I'm not sure if our textbook mentioned this. I don't think our textbook mentioned this, but it would be nice for us to identify. Okay, note the volume in 3 dimension of this ball will be triple integral from 0 to 2 pi, 0 to pi, and then 0 to a of r squared sine phi d rho d phi d theta. Is it right? Okay, now if the rho is constant a, right? If the rho equals to constant a, now then what happened is this rho squared now becomes a squared, but we don't integrate that with respect to the rho anymore because it's already constant. Okay, if the rho equals to a, then the surface area instead of volume is integral from 0 to pi, integral from 0 to 2 pi, integral to 0 to pi of a squared sine phi d theta. Okay, I think what is more important is the following. Okay, the surface parametrization. This is something good to memorize because we see this a lot in the next section. Parametrization of a sphere with radius a is given by this. I'm sorry, r phi cross. I'm sorry. r phi theta be a sine phi cosine theta, a sine phi sine theta, and a cosine phi, right? Now, after this and that, you will see that the magnitude of r sub phi cross r sub theta equals to a squared sine phi only. And that is actually comes from remember the Jacobian. Okay, that's basically the Jacobian in triple integrals, right? Okay, the Jacobian rho squared sine phi, but we fix the rho by a. Okay, so the double integral, instead of like instead of with rho squared sine phi, now the double integral now becomes just a squared sine phi. Okay, rho phi do theta. Okay, that's something worth identifying though. Okay. Okay, I'm basically done with this section, but because we need to do some, you need to practice a lot, let's do some examples, okay? But because I do some examples here, then in my supplemental videos later on, I will do much less, okay? You still need to practice though. I will do some even numbers. You will do odd numbers so that you can check with the back of the book. Okay, now number 4. Number 4. The question is to identify the surface RU phi equals to 2 sine U, 3 cosine U phi, where the phi is from 0 to 2. Okay, so then R sub, actually we need to identify only. Well, then you see the x component, x over 2 is sine u, y over 3 is cosine u, and together that gives us x over 2 squared plus y over 3 squared equals to 1, right? And then the z component v is independent of x and in x and y, right? So on the xy plane, this is actually an ellipse, right? This is 2, -2, this is 3, -3 here. And because the z component is independent of u, then it will just give us a cylindrical, I think I should say elliptic cylinder. It will be an elliptic cylinder. Okay, that's for number 4. Number 6. I have to admit, your success in this section depends heavily on how good you are with your curve parameterizations and even your two-dimensional curve parameterization in your calculus 2. Okay, I need that very much. I need that very much. Now let's see, number 6, you have s sine 2t, s squared, s cosine 2t. Notice that the x component squared plus the c component squared give us s squared, right? Which is the y. You see that? Okay. So the equation, basically the surface can be written as y as a function of x squared plus c squared. Right? Notice that this is actually a paraboloid, opens in the y direction. Right? If you have our x and z gives our theta, think of this as an inverted polar. Instead of x and y give you r theta, you use x and z give you theta, r theta. Okay, so then all of a sudden you have, this is your y and this is the paraboloid r, right? But it opens in the y direction. Okay, like that. That's for number 6. Let's see more. Find the parametric representation for that surface. Number 20, the easiest one. That's just the plane, right? Number 20. So R u v equals to the point that it contains plus u times one of the factor plus v times the other factor. If we put them together, there will be 2u minus 3v for the x component, negative 1 plus 2u plus 2v for the y component, 5 plus 4u plus 5v in the next component. Okay. Number 22. Part of the ellipsoid that lies to the left of xy plane. So you have an ellipsoid. You have an ellipsoid that is part of that, but it goes only to the left. We just want the one on the left hand side. Okay, just the one on the left hand side. If so, we can make it a function of c, a function of y. You solve for y, and then the y is negative, right? Can you imagine that? The left hand side of xc plane. The left hand side of xc plane means the y is negative, less than equals to 0, right? So we can do it this way. So you solve for y. So y 2y squared equals to 1 minus x squared minus 3c squared. Okay, so y equals to negative square root of 1 minus x squared minus 3c squared over 2. You see that? So we can parameterize that using x and z, right? So r x z equals to x negative square root of 1 minus x squared minus 3c squared over 2 and c. Okay, number 24. I think this one is difficult. Number 24. Number 24, that's actually part of the sphere. Part of the sphere. X squared plus y squared plus c squared equals to 4. Okay, I'm sorry, equals to 16, not 4. I happen to look at number 23. Okay, but the z is between -2 to 2. Okay, so think of that as a sphere, but that you cut between 2 and -2. Okay, so we are only dealing with this, what you call this bangle, maybe you want to call that, right? This part here. Okay, that part here. But notice that's not a function of x and y though. I mean, z, we cannot write it as a c as a function of x and y, right? Okay, now, but earlier we learned that we can parameterize a surface using phi and theta, right? Okay, so let's parameterize it that way. So phi and theta equals to 4 sine phi cosine theta 4 sine phi. Let me use this phi, this style right now. Sine theta and then 4 cosine phi. Okay, but then we limit the phi. Notice that if this is my z component, z axis there, my c has to be up to 2, right? Okay, but the radius rho is 4. This is 4. This is 2. What is the angle here? The phi equals to pi over 3. Is it right? Okay, down to c equals to -2. So the phi will be 2 pi over 3. Is it right? Okay, so we will get the same thing, but we limit the phi now is from pi over 3 to 2 pi over 3. Okay, that's how you make it part of the sphere instead of the full sphere, where the phi is from 0 to pi. Your phi now from pi over 3 to 2 pi over 3. Okay, let's go on more. The equation of the tangent plane. Number 34. I basically do all even numbers already. Huh? Okay, so in my supplemental videos later on, I will do some odd numbers. Okay, I hope that's okay. Yeah. But for odd numbers, you have the solution at the back of the book already. Number 34, we have r u phi equals to u squared plus 1, phi cubed plus 1, u plus phi, where and we need at coordinate 5 to 3. Okay, so let's find the u phi first. R u phi equals to 5 to 3. Okay. So u squared plus 1 equals to 5 implies u will be 2 or u equals to -2. Okay, phi cubed plus 1 equals to 2. It implies phi equals to 1, huh? Okay, and then u plus phi equals to 3, right? Which means u equals to 2. Okay, so r 2 comma 1 equals to 5 to 3. Okay, next, how about r sub u? R sub u will be 2u 0 1. R sub phi will be 0 3 phi squared 1. Okay, So actually you can compute it this way. So it means R sub u at 2 comma 1 will be 4 0 1. R sub v at 2 comma 1 will be 0 3 1. Okay, so the cross product. So instead of you do the cross product first, then put in 2 comma 1, what you can do, you put 2 comma 1 first, and then you do the cross product. Okay, add 2 comma 1. That will be -3, -4, 12. Okay, now this is the factor normal to the plane. Right, this is the factor normal to the plane. So equation of the tangent plane will be -3 times x minus 5, -4 times y minus 2, plus 12 times c minus 3 equals 0. I think I can, no, I cannot reduce anyway, huh? Okay, so this will be -3x plus 15 minus 4y plus 8 plus 12c minus 36 equals 0. -3x, -4y plus 12c, that's 23, that's minus 13, huh? Because 13, like that. Okay. That's for number 34. Let's do number 36. Number 36, we have R u v equals to sine u cosine u sine phi, and then sine phi. At u equals to pi over 6, phi equals to pi over 6. So u at u equals to phi equals to pi over 6. Okay, let's do the coordinate first. So pi over 6, pi over 6. That will be sine pi over 6 is 1/2. Cosine pi over 6 is radical 3 over 2. So this was radical 3 over 4. And this is 1/2. Okay, I'm sorry. Yeah, that's right. Now then, how about the R sub u? R sub u will be cosine u negative sine u sine phi, comma 0. Okay, and then R sub phi will be 0 cosine u cosine phi cosine phi. So the cross product, or you want to plug in 0 for the pi over 6 first? Let's do that first then. So R sub u at pi over 6 comma pi over 6 will be radical 3 over 2 negative 1/4 0, and R sub phi of at pi over 6 will be 0 3/4 radical 3 over 2. So the cross product, therefore, will be negative radical 3 over 8, negative 3 over 4, 3 radical 3 over 8. So this is the factor normal to the plane. You know what? We just need a normal factor, right? So let's multiply this by LCD 8. That will give us negative radical 3, negative 6, 3 radical 3. Okay, so the tangent plane, equation of tangent plane is given by negative radical 3 times x minus 1 half minus 6 times y minus radical 3 over 4, and then plus 3 radical 3 c minus 1 half equals to 0. Okay, and then from there we simplify, which I don't think is a nice simplification. And then what is that? Plus 2 radical 3 minus 3 halves equals 0. Okay, now that's the equation of the tangent plane at that point. Okay. Let's see more. Is there anything else we can do? I think it's about the surface area, huh? Okay, I will do one question for the surface area, and then the rest you look at the supplemental video. Okay, let's say we want to do this part of the cone between y equals to x and y equals to x squared. Oh wow, part of the cone, but this happens to be parameterizable regular way, right? Okay, this just the domain of the integration later on is bounded by y equals to x and y equals to x squared, right? So y equals to x and y equals to x squared. That's the domain of integration. Okay, while the cone itself, we can easily parameterize that using xy, or xy equals to xy square root of x squared plus y squared. Or you can just parameterize that regularly, right? You can just say that c equals to square root of x squared plus y squared. C sub x is x over square root of x squared plus y squared. C sub y is y over square root of x squared plus y squared. Okay, so c sub x squared plus c sub y squared plus 1, you will see boom, that's equals to 2. Okay, so the area of that surface S, which is the cone, in 3 dimensions. Let's try to imagine that. So in 3 dimensions, that's the domain, but the cone will be maybe like something like that. Okay, it's a curve a bit. Okay, this is the D, this is the S here. Okay, so there will be double integral over D of 2dA. Well, that's basically 2 times the area of D. How to find the area of D? You do it yourself, right? That's an easy integration, I believe. let's integral 2 times integral from 0 to 1. Integral from the lower bound is x squared, the upper bound is x dy dx. Okay, oh, you can just do it with single integral for God's sake. Okay, 2 times integral from 0 to 1 of x minus x squared dx. So that will be 2 times 1, 6, right? 2 times 1 over 6, which is 1/3. Okay. Suggested homework from this section. So for 16.6, suggested homework will be from number 3 to number 6, 19 to 26, 33 to 36, 39 to 50. I only did one example there, but you should do more. Okay, and 61 to 63. Okay, I think that's for today.